On March 26, the collision with the cargo ship Dali led to the bridge's collapse. The NTSB's drone footage offers us a unique view for various operational insights. As an engineer, I'm caught between the sadness of loss and a spark of curiosity to find solutions. How I wish the initial drone survey had embraced the full potential of photogrammetry, capturing the scene with the orbital trajectory and overlapping oblique shots at varying altitude, topped with a series of nadir images for comprehensive coverage. Instead, we work with traditional drone footage. Here's where we bring the footage into play. After selecting our file, we set the interval for frame extraction. I'm going with 1 frame every second. The system then begins to convert these images. At this point, we can also perform a quick visual inspection images to ensure everything is on the track. As we examine our first 3D model, it is time for a quick quality check. We notice the measurements come back unitless, hinting at a scale issue due to many unknowns. So how do we tackle this without physical access to the measurements? A eureka moment comes from the visible cargo containers on the ship. Their standard lengths of 40 feet, self-explanatory, becomes our makeshift ruler, offering the exact reference we need to correct the model's scale accuracy. Our next step involves refining our 3D model by identifying tie points across the images for 2 main reasons. First, these points help align and stitch the images together more accurately. Second, they serve as crucial markers for scaling, ensuring our digital model matches the real-world sizes. We focus on specific, easily recognizable features, like certain cargo containers that appear in multiple shots. By marking the same corner across these images, we establish consistency across our datasets. With about 10 tie points selected, we move on to setting constraints based on known distances, such as the 40-foot length of a container, to inform the software of the scale it should apply. This allows us to achieve accurate measurements across the model, like confirming the ship's length at around 300 meters. Now we encounter a challenge with the ship's rear appearing blurred or melted. Our solution would be high-quality images from the other sources. So searching in the internet, the Baltimore Police Department Flickr's album came up, and despite potential issues from varying zoom levels, advanced features combined with our manual efforts of tie points and stitching together enabled us to integrate these images successfully, sharpening the previous unclear areas of the ship. This process significantly enhances the model's accuracy and detail, transforming it into a vivid, informative representation of the incident scenes. The fly-through reveals that, while the image distribution was adequate for its primary goal of providing visual documentation for planning purposes, it falls short of the comprehensive coverage needed for our 3D modeling objectives, particularly due to its concentrated focus on the bow's collision point and not encompassing the entire scene through varied trajectories. We explored the model with the various measuring tools, and toggling between mesh views, textured or untextured, and point clouds, all scaled accurately. By applying Lumo AI's Neural Radiance Field or NeRF technique to the drone footage, our goal was to create a photorealistic model. This method excels at rendering shiny surfaces with lifelike quality, but doesn't offer the same level accuracy in measurements as photogrammetry does.